Everyone, I wanted to continue our discussion on sharding today. In the last class, we looked at mitosis, which was a sharding system for permission blockchains. So there were only a few set of nodes who had permission to become consensus nodes, and mitosis had some ideas about how to have multiple shards, how to divide one shard into multiple shards, to combine shards into one, and so on, right? But the question is, can we shard permissionless systems? Okay, so what if anyone can join, anyone can become a consensus node? Can we have a sharded system there? Right, so people have been thinking about these systems too, and today I wanted to talk a little bit about RapidChain. So RapidChain was a paper published in CCS 2020. Sorry, I think it was 2018. Okay. So let's think about it for a moment. So what are the permissionless protocols that we are familiar with? So we have things like proof of work, some sort of proof of stake type protocols, right, which are used in permissionless systems. And here you have to have some sort of a resource in order to vote, either hashing power or stake and so on, right? And this resource should be impossible to arbitrarily replicate, so it prevents a Sybil attack. And this is something we are very well versed with. Okay. So can we have multiple chains using proof of work and proof of stake? Okay, and we'd have to think about it. So if you have, let's say, multiple chains, how would you divide proof of work among all of these? I mean, so how is somebody supposed to do proof of work on multiple chains? Because right now, if you're creating a block here, then you're not creating a block here, right? Or what do we want to do? Do we want to have a system where somebody does, let's say, proof of work on multiple chains simultaneously? Okay, and it's sort of like how we had voting chains in Prism. Should we do something like that over here, right? The question is, what do we want to achieve? I mean, so in theory, of course, you could have somebody who's mining on all the chains, right? We have a different target for different chains, and one of the issues becomes that do you want a single miner to be involved with multiple chains? So should it be involved with creating blocks, or storing information, or being involved in the consensus for multiple chains? Okay, so and the point is that if a single miner is involved with multiple chains, then why not just have one chain? I mean, the thing is, because anyway all miners are working, if you have a single chain, all miners are working on that chain. So what would this buy us? And one of the things which we may get is that by having multiple chains, we may reduce forking as opposed to, let's say, having a very large block over here in a single chain, right? So if you, so the question is, what we want to really achieve. And really we are looking at performance. So one is we want to increase the throughput of transactions, and we would like to reduce the latency. Okay, so how are we going to achieve these goals? So one way is that we have, let's say, a single chain with very large blocks. Right? Versus you have multiple shards with small blocks. And the question is, are these equivalent if you have, let's say, miners working on multiple shards simultaneously? Right? Somebody could potentially create blocks over here for all of them, and of course, depending on which proof of work he solves, you can have a different target range for these different shards. He will release that particular block. We could have something like that, like we did the voting blocks in Prism, right? The thing is, would there be any difference? So one of the things is, let's say the throughput might be the same over here, but the forking over here would be higher because you have very large blocks. Here you have small blocks. It maybe this block is 10 times the size of any of these blocks here, and you have 10 chains over here. Right, so the throughput would ideally be the same, but the problem is you would have more forking here. But of course here the flip side is that you have to deal with intra-shard transactions. Inter or cross-shard transactions, right? What if money has to be sent from one chain to the other? That becomes a tricky issue, right? Also we would have to worry about proof of work. So the proof of work is not final. So it's like a consensus in probability. And it's not final. So that would become very tricky. So suppose somebody shifts money from here to here, right? And suppose this shard thinks, okay, the money has come here, and let's say money keeps getting spent over here, but then this original block which shifted the money from here to here is removed due to some sort of an attack or forking or something like that. Then we'd be in trouble, right? So it's very tricky to do that. If you have something like PBFT running in every chain where it's final, under a particular security model, once consensus has been achieved, it's done. You have safety guarantee. Okay? Here you don't have a guarantee for safety. It's only some sort of probability that you have that the block will remain there for forever. Right? So how do we deal with those sorts of situations? It complicates the cross-shard situation if blocks might disappear from one chain, and the other chain expected that block to remain there forever. Right? So this using proof of work is non-trivial when you have a sharded system over here. Right? And Also, you might wonder why have a single miner working on multiple chains? Okay, so the thing is, you want to scale up Bitcoin, let's say by several orders of magnitude, let's say 3-4 orders of magnitude. Instead of 7 transactions per second, let's say you want 70,000 transactions per second. And in that case, do you really want an individual miner to be dealing with something like that? Because then his storage and his computational needs go up, right? So these are questions we have to ask. Do you want a single miner to be messing around with multiple chains in a sharded system? Because if you can have a miner focused on a single chain, then there is going to be more scalability. He might need less memory, less storage information, or less information on his disk or in his RAM, right? Less maybe computational power to verify all the transactions, right? And it may scale things up better. Okay? So with all these in mind, let's start discussing about RapidChain. Okay, so RapidChain is one of the clever ideas in order to improve performance. Now RapidChain has many different parts to it, and there are many small optimizations they make in order to improve the performance, but we will look at it more from a high level. Okay, so let's think about it. So what are the first, let's say, what are the drawbacks of POW? So drawbacks of POW, first of all, you need small blocks. What do I mean by small blocks? It's really that the propagation time of blocks should be small compared to the interarrival time of generation. Okay, so Bitcoin block might take 10 seconds to propagate in the network, but the interarrival time between blocks is 10 minutes. Okay. So if you don't do that, there's be a lot of forking, and so small blocks means less throughput. Also, we have delayed confirmation. Right, and when you have a delayed confirmation, I mean, it affects the performance you're giving the application. I mean, a user may want quick confirmation, right? So these are some issues that we have with proof of work. But with something like PBFT, we don't have this issue. So PBFT is used for permission systems, and you can have larger blocks, and there is low confirmation here. So as long as the leader is honest, things are going to be fine. The blocks will be confirmed very soon, right? It's just a few round trip times, and then you have confirmation, right? And once you have confirmation, the next block can be sent out, right? So you have higher throughput and quicker confirmation. So the question is, can we use something like PBFT in a permissionless system? Right, and already we've seen some ideas in Algorand. Of course, Algorand doesn't use proof of work, but it uses a method of creating committees, right? And that helps improve the confirmation time. Okay, because but of course, Algorand is a little bit tricky, that you have multiple rounds and so on, right? And there's a new consensus protocol used over there. But several people are wondering, can you use something like PBFT in a permission system? Because if you can do that, then maybe you can improve the performance directly. Sorry, if can you use PBFT in a permissionless system? So RapidChain, of course, is not the first one to do this. So they reuse some ideas which were there earlier. But yes, the answer is yes, they want to use something like PBFT in a permissionless system. So how do we do it? In PBFT, you have some sort of an identity, right? So you have some sort of a public key. And normally there are just a limited number of these, and those nodes get to do consensus. In a permissionless system, you have the Sybil attack problem, that anybody can create arbitrary number of identities, right? So the question is, can you use POW to limit the number of such identities and then use something like PBFT after that? So you create a limited number of identities. Okay, and then use these in a BFT protocol. So RapidChain doesn't actually use the PBFT protocol. So PBFT, of course, we know from Castro and Liskov. We studied it in the previous course. They use a more recent BFT protocol which has better performance, right? But under certain more restrictive network delay models and so on. So how are we going to do this? So there is a POW puzzle, and let's say there is a limited amount of time. So POW puzzle is created here, and this is the deadline. So there is some time period over which you have to try to solve the POW puzzle. So various miners can try to solve it, and let's say somebody gives a solution here, a solution here. Right? And let's say these are they give various public keys we mentioned it in the solutions. Just like you have in Bitcoin, in the Coinbase, you record your public key. Right? And suppose there are this many solutions present, right? So obviously somebody with more hashing power might be able to generate multiple solutions like this, which crack the puzzle. Okay? Now at the end of this, there are now n identities. Okay, so we have n identities now, and with this we have solved the Sybil problem, and that nobody can create arbitrary number of identities. So after this, after the deadline, we can use the identities for PBFT. I should say some BFT protocol. Okay, so it's a clever idea. Now these people can get together and they can use any BFT protocol in order to create blocks. Okay, so they use the identities for BFT, and here in this period, okay, you can have large block sizes and you can have low confirmation times, because the BFT protocol is finite, right? So there are several questions which probably are coming into your mind. So how do we know that the BFT protocol is going to work? Because the BFT protocol has some assumptions, some security model is assumed, and is that going to be true when in this system, right? So we are starting with a permissionless system and we are trying to convert it to some sort of permissioned system, right? And also the question is that where are the shards? So we haven't yet talked about it. So let's think first of all, for us, suppose it's a single system, suppose it's single shard, and we just have POW being done here, and you could think of converting Bitcoin to a system like this, where initially people just solve proof of work and thereafter they do something like PBFT and they generate blocks pretty fast. Okay, so various issues have come to the fore. So one is, what if n is large? So BFT protocols use typically are heavy in communication. At least PBFT we are aware of is like order of n square, and suppose you start this thing and then you have too many people who have submitted solutions, then this is not going to work, right? So we'll have to limit. Of course, we might say that we are going to set the threshold so that based on the total hashing power in the network, and you ensure that a small number of them are created, right? Of course, then there is the worry that a lot of the small miners may get left out. That is something we would have to worry about, that maybe only the big miners get in, right? The small people get left out, and then they have no incentive to continue with the protocol, right? Okay, but anyway, there is this basic issue over here, right? And secondly, suppose our less than 1/3 of identities Byzantine. Okay, so 1/3 is of course required for PBFT, but of course the BFT protocol which RapidChain uses can tolerate 1/2, I mean anything up to 1/2 of identities being Byzantine. Okay, so it's a more recent protocol. And I mean, so the reason why PBFT folks considered 1/3 was because they looked at an potentially asynchronous system, and they wanted to guarantee safety. Right? But if you have a synchronous system, people have shown you can go up to 1/2. Right? But anyway, whatever it is, you need to have a less than a certain number of nodes to be Byzantine. Otherwise, these protocols are not going to work. Okay, so this is another issue that we will have to consider. Well, let me write down the earlier point which I mentioned. What about miners who don't solve the puzzle? Are they left out forever? And then what about multiple shards? Because that's really what we are after. So let's look at this second question. How can you be sure that less than 1/3 of the identities are Byzantine? Because if that's not true, then we are in trouble. Okay. So what is the trick to be used here? So answer to question 2. So we start out with the POW miners. Right, and let's assume that all have equal mining power. I mean, there's no loss of generality there, because if somebody has more mining power than the others, you just say that he has multiple of these nodes, right? But let's say that suppose all have 1 unit of hashing power. Right? And we have to assume that less than 50% are Byzantine, because otherwise we're liable to a 51% attack and we're in big trouble, right? But anyway, so suppose we say that there are less than 50%. Now some of these are able to, let's say, solve the puzzle. So let's say that this one solves the puzzle, this one, and so on, right? So a random number of these are chosen. Right? So the question is, what is the probability that these are going to, what percentage of these are going to be Byzantine? I mean, this is a straightforward problem. I mean, depending on how exactly we are going from here to here, whether we are exactly choosing a certain number, or it's a random number of some n, where n can vary a little bit, right? But essentially we are sort of like choosing any of these in a coin flip experiment, right? And we want to find out what's the probability that a certain number of those selected are Byzantine or not. Okay? And in general, suppose we are given something like this, then there is a non-zero probability, I mean a fairly large probability even, that we would have larger than this threshold 50% being Byzantine. Okay, so this is going to be an issue, and we are likely to have large fraction maybe I should say likely to have greater than 50% let's say with a large probability. Okay. So this is going to be an issue, right? From half being Byzantine, you randomly choose them and then you say I want less than 1/3 to be Byzantine. I mean, in fact, you will have greater than 50% even Byzantine with some reasonably high probability. So this is not going to work. So 50% is too high. We need less than that. In fact, you would need much less than 1/3 to be Byzantine to start out with. Okay. This is an issue. So what is RapidChain going to do? So RapidChain first of all is going to use a BFT protocol which tolerates less than 1/2 Byzantine, right? Okay, and it's going to assume a synchronous network. Okay, unlike asynchronous for BBFT, right? So now we have bought ourselves some leeway. Instead of having this requirement of 1/3, I have only requirement of 1/2 being Byzantine. But still 50% again is too much. I mean, there may be high probability, 5% or 10%, that the subset would have more than 50% which are Byzantine. Okay. So what they are going to assume less than 1/3 of hashing power is controlled by Byzantine nodes. Okay. So now you can show that with high probability, you can mathematically calculate that if initially you are starting out with less than 1/3 being Byzantine, then with high probability you end up with a pool of nodes where half are less than half, strictly less than half are Byzantine. But it's not a guarantee, it's just with high probability, right? So maybe 1 in a million chances you will have this having more than 50% who are Byzantine, right? And of course none of these protocols like RapidChain, and there are others like Elastico and so on, none of them are considering rational miners. So the model is you have honest and you have Byzantine, right? Whereas Satoshi of course was probably envisioning a situation where miners are rational, so he gave them enough incentives to sort of behave honest, right? But anyway, right now we are going with the Byzantine versus honest model, and we are saying if less than 1/3 are Byzantine and you randomly pick n out of them, then with very high probability you can show that less than half of them are going to be Byzantine. Okay, for some reasonable size of n. Okay, if you choose a single node from among these, then there may be a high chance that that node is going to be Byzantine. Right? But if you choose, let's say 50, 100 of them, then you can show that you're going to have less than half Byzantine with high probability. Okay, so this is one basic idea which rapid chain is going to use. Okay. Then let's look at some of the other questions that we talk about. Okay, so there is this issue: what should n be, right? And what should be the size of this shard? And the size of the shard, I mean the size of consensus set. Okay, the set of nodes which are doing consensus, and they call it M in the paper, not N. And if so, suppose you have N nodes selected by POW puzzle. Okay. So initially we were considering just a single shard where all of them are in the same shard. Now we want to have multiple shards. So what they set is M is equal to 20 log n. I'm not sure if the log is to base 10 or, but let's think of it as log to the base 10. Okay. So this is fairly small. Even if you have n increasing to a large number, this number doesn't increase too much. So you end up with a somewhat of a small size set, right? So even if n goes up by a factor of 10, your M for number of consensus nodes per shard is going to be small, right? And so the number of shards is equal to n divided by 20 log n. So what does this mean? That if you let's say if you have more number of nodes being selected, then the number of shards goes up higher. Right, so this is interesting thing, and so you might say, what if lots of people are joining the system, and suppose we keep the POW puzzle threshold the same, right? So suppose you keep the puzzle the same, then if more and more people are joining and doing hashing, then effectively you're going to have more and more number of shards, and that's going to scale up the throughput of the system. Okay. Okay, so we don't have to worry about having a very large set for doing BFT, because we are only looking at log n of the nodes being selected. Okay, so we've figured out some of these questions. So we've sort of addressed some of them, especially the first two, right? And of course, the question is, how exactly do we have multiple shards? How do we divide up these n nodes into shards, where each shard has only a subset M of those nodes which are taking care of consensus?